the title is analyzing and modeling curves or curved responses. So it will be with Functional Data Explorer, but we want to make sure folks don't get turned off by that terminology. Specifically today, we are going to look at some creep curves, and that's going to be with these HDPE, high density polyethylene shipping containers. This is a real case study that I lived. The company that designed and built these shipping containers here that you see in the upper right recently contacted me back after many years and said, we're still interested in some of the work you did with us back in 1996. So this is a 1996 data that I pulled out of a Word document. So I was able to get pictures and data actually with some cool add-ins into JMP. So we're going to take a look at this data. However, I told them, way back then, we didn't know, the team of engineers we were working with didn't know anything really about statistics nor design of experiments. So I suggested we swallow our pride and actually bring in some big guns. So that's why Mr. Christian Stopp is here today as our resident statistician. And I even roped in Marilyn Wheatley at the finish line here to join us. And she's on that statistician side as well. I'm just a process engineer. So, well, thanks for you guys joining me, Christian and Marilyn. And Christian, this case study is what I was describing with you last week when I was mentioning these creep curves and polymer testing and stuff like that. So hopefully, or what do you think? Do you think some new tools or this Functional Data Explorer could help us?
Yeah, I do. And yeah, thanks for reaching out there, Clark, for a little bit information. I was taking a peek at the Google just before we chatted to get an idea of maybe the kinds of things you might be talking about before we met, just to get a sense of what's going on. And I saw these different kinds of curves. So different types of shapes. And sometimes when I think about modeling these types of data, there's a kind of two different approaches. And I tend to think of it like when I go to buy a suit, right? You've got certain types of models that they're already predefined, and so they fit certain specific types of structures. And then so that's a top-down approach. And I think of that like when you go and you buy a suit off the rack, where I'm just trying to find the best suit that fits my body. And that's what you're doing with the model, is you're putting the best model, trying to figure out which model fits the data best.
Gotcha.
Yeah, the reverse is doing the bottom up, where I'm going to the tailor and saying, hey, I got a weird looking body type. Can you put the suit, help me define a suit that fits me? And so that's where the Functional Data Explorer comes in, is it says, show me the data, we'll work from the data and the variability there, and we'll build a model kind of from what you've got in your actual data. So do these kind of look like what you were talking about there?
Well, yeah, and what you're describing, I think I do need a custom suit. And what I didn't know you knew so much about polymer material science either, being a statsy guy. So these different testing techniques, differential scanning, calorimetry, TGA, tensile testing. Oh, I've overlaid thousands of these trying to find information. So
ouch.
There's not creep on here, but yes, we're using some of this. So if you think you can analyze these curves, I think we can do it with the creep curves.
Great. Yeah, that's kind of the goal of the functional data analysis, or the curve responses, is to model these types of things. What have you got as far as like your curves, your creep curves?
Yeah, let me review the problem that we're trying to solve today. And it's essentially too much creep, and that's not the Radiohead song nor the TLC. We called our lab the TLC Creep Lab back in the 90s. So this company, with their polyethylene shipping pallets, they're experiencing excessive creep in warm environments. So shipping, all these oranges down to Maryland and Arizona, this is real. So under temperature, these pallets would start to sag and bow out, and they would eventually interfere with the walls of this trailer. And guess what you can't do when that happens?
I'm going to guess unload those little crates there.
Can't bring the forklift in, you can't unload. So what end up happening is sawzall these walls off and unload.
Ooh,
so
that sounds fun.
Super expensive. Now the company they know they need to improve the product, but their question is, in the short term, can we mitigate this creep here by analyzing some historical data that we already collected? So leverage some data it's not a lot, but can we understand some inputs and maybe put some operating controls around how we ship these goods or where we ship these goods to hot or cold environments? So that's creep. It's this excessive deformation under temperature and load.
Cool. Yeah, it sounds like you're getting a lot of orange juice out of there too, but with the oranges mash in there. But yeah, it reminds me of like frosting when you make a cake, right? And you heat up the cake. You frost the cake before it's done cooling, you know.
Oh,
and
yeah.
You put the layers on top of one another, and the frosting just kind of melts out. Yeah, it sounds kind of like that.
That's my birthday cake in August every year. So
At these temperatures, yeah.
So how about tell you a little bit more about creep, how it's measured?
Yeah, that sounds like a good plan. Tell me what you do.
Here's the measurement setup here. And we start with a dog bone. I mean, that's my dog Estes. She doesn't like this shape very much, but we load up this dog bone. We actually attach an extensometer on there. That's the device that's going to tell us the displacement or how much this dog bone stretches. We load that up into a tensile tester in Strawn MTS, and you pull to a certain stress level and hold. And then over time, we're recording that deformation. So what you see here as our response is we see a deformation, and apologize. Remember, this is a word graphic that I got here. It's hard to see, but we have deformation here, and then we have time. And what you see is these multiple curves, those are at different stress levels. So we get this deformation versus time. Does that make sense of what we're looking at, Christian?
Yeah. No, do you ever throw Laffy Taffy in there? Just out of curiosity.
No, but that's a viscoelastic material too. So absolutely.
I always come back to food.
We can do that.
Yeah. That's it's interesting plot you got there. It looks kind of like you've got different curves with different shapes, and it looks like you might even have an experiment that you were doing to elicit those curves. Is that look about right?
We did. We had an experiment. And I know you're going to ask me something.
Yeah, how are you analyzing that? Or what are you doing?
I was waiting for it. Here comes Mr. Statsy asking the engineer how we did this. And I'm going to come clean. We had some input factors, but we didn't do a formal DOE. To be honest, I didn't know anything about that. So here's our factors that we had. We actually have two materials, virgin and recycled. And then we have temperature at 3 levels. And then stress at 3 levels. And literally how we were analyzing this is overlaying this in Excel. So for example, on the left, it's recycled material, and then the temperature is fixed, and we varied the stress level. So we're trying to understand the impact of stress between these curves. On the right, similar kind of approach, but we switched the materials, and then we froze the stress level and changed the temperature. And I'm afraid I know what you're going to say now.
Yeah, you're fixing one of the things and modifying the other. It's curious about interactions in there too. So something that we may have to consider there. How are we going to think about that?
It's kind of like OFAT, huh? One factor at a time. I know we didn't do it right, or we could have done it better. So, well, I got the data we got. So what do you think? Do you think we should take a look at that and see what the FDE can do for us?
Absolutely. Yeah, Jim's got great tools. Let's throw it in there and see what we got.
So here's the data table that I got, and here's the setup. I have my X and Y, so my time and my strain deformation level. And then here are those factors. Now, I don't know. Again, we didn't design it, but maybe there's something in here. And then we see the material type. And then what I included here in this stacked format is a test run ID. So this, to me, lets me know that whole curve identifier.
Right.
So that's kind of what we got set up. Hopefully that's a decent format to use.
Oh yeah, well, let's take a peek at it. One of my colleagues used to say, plot the data, plot the data, plot the data. So let's throw it in Graph Builder.
I can't disagree with that. Graph Builder is my favorite here. So I got an initial script that I just did a plot and just did a continuous, connect through here. What did you want to take a look at in Graph Builder? What else?
Yeah, well, one of the tools that kind of underlies some of the models that's in the Functional Data Explorer that we'll see is the spline. So if you want to throw a spline on there, we can look to see how varying some of the parameters of that spline fit the data.
Oh,
Some
I
kind of
love
shapes you got.
messing with the lambda here. Linear all the way. Okay.
And it looks like you've got a few of basically the shape is pretty common across them, except right there at the end where you've got like a bend. So you might have a few different shapes in there that Functional Data Explorer will tease out.
And it looks like, I think you can kind of see the slope start to increase here in some of these conditions. I'm going to goof around real quick and do a moving average fit. Ooh. Oh, so there's different ways to kind of model this. Okay, but you're saying splines looks pretty good. Okay, great.
Yeah, you want to check out the new tool?
Yeah, let's take a look. Where do I go?
Analyze. Right there, and then specialized modeling for your sensor or spectral data, and then Functional Data Explorer.
Functional Data Explorer. Okay, now X and Y, I think I can figure that out. Time and my strain deformation. These look new to me.
You got an ID like you were doing in Graph Builder, so you can throw that in the ID function.
Oh, that's letting it know which function is associated with that column of data. Okay.
Yep. And then those experimental conditions that you use, so stress level through material type, what we can do is pass that information into the Functional Data Explorer and then use that on the back end to see potentially if some of those changes you were making, if they are able to tease out any effects on that shape of that curve.
Okay. Where they go into the Z here?
Yep. Supplementary.
Okay. Supplementary, and seems like we're ready to roll.
Okay.
Okay. Now, I love tinkering, so I'm already going to start tinkering here.
Tinker away.
It's Jumps interactive. So, it already does another visual and it breaks out all my functions. Cool. I see. Uh-oh, what's this? What's this stuff right here?
Basically, it's just an overall idea of what's the mean function of the data. So again, getting to that idea of what are the underlying shapes is that the mean function there on the left. And then the standard deviation function is kind of giving you an idea of where the variability is in the function.
Okay. Okay. Well, where do we start here? So it's a good visual, breaks everything out. Now where do I go?
I'd start, modeling is going to be iterative. So I'd start just at the top easy button, red triangle there.
All right, red triangle. I know we always got to go to the red triangle.
Models? We'll just throw a model on there and see what happens. You got different choices here. So that the spline fit that you were doing in Graph Builder is part of what underlies that idea behind the B and the P-splines there.
Okay.
So they'll be applicable to most of the data that you'll be interacting with. I expect they'll work well here. With the Fourier basis, if you're thinking of things like seasonality or maybe recurrent patterns of, sine wave type things, that's pretty good for that.
Okay.
And then your wavelets, that one's new in 17, and it helps you fit really sharp peak data. So you don't have that, so we can look at it, but I would start with the simple ones and go to beta spline first.
Okay, so it sounds like, clearly we're not Fourier wavelets. So B-splines, okay.
Hit it.
Look out, I'm gonna start tinkering because I like to mess with the interactivity here. So I'm moving this thing to the, what's happening with these, what's this knots thing?
So in the background, Jump fit, I think 24 different models, and it gave you the best one right off the bat. Those black diamonds you're moving around, those are the knots.
Oh, okay.
And then Jump is fitting different types of curves in between those knots. So instead of one big graph like in Graph Builder, you've got, it looks like, 14 different functions in between there.
Now I see what you mean by knots. So as I shift this, I just click on step functions, and that's telling me it's doing the fit between that knot. Okay, I see how that's working. And now I can just switch between these different degrees here. Now, these curves, I don't know, they don't look like a creep curve. They look like an elephant or something. So that fit's not very good. It's looking pretty wonky.
Wonky, great word.
I know it's not engineering related, but it is wonky. Can we clean this up or improve it?
Yeah, there's a few ways of doing that. One is you can, like you were doing, you can play with the knots and define different steps, different functions there. Another is to go into the model controls right there.
Oh, I see this. That's collapse. Okay, model controls.
Yeah, and so you had 5 knots was the best model. Maybe you can find better models that are around there. So you can just do a range of like 1 to 10 because the other models.
Okay,
yeah.
Range 1 to 10. And then we know that step function looks the worst, right? I don't have to fit that, right?
Yeah, you can leave it in sometimes if I mean, it's pretty fast usually, but you can take it out.
And then hit go if we want to take a look at that grid. Okay.
Oh, so it's telling you 4 knots is the best based on the options that you selected there.
But this, how it's being fit here, this, I mean, that's not a creep curve. Again, it's got the elephant trunk here. That's not right.
Yeah, it's that cubic model, that degree 3, pulling that down on the back end. So
yeah, a little bit better, but still not really good fit. Where else can we do?
I noticed that a lot of your runs there, they don't all finish at the same time. So you've got different time lengths for your different experiments, which is probably fine for what you do. It's just like the models ends up affecting the model on the back end.
You are correct. Highlight another deficiency of us engineers way back in the mid 90s. Yeah, I didn't control it. You're right. See, I have different endpoints between here. So what's your suggestion? Can we still process the data?
Yeah, and to be fair, in some cases you don't even aren't even able to structure those to be the same time. So this where some of these other tools come in really handy. Like a conversation I had recently was that align tab. Yeah.
Okay, align. Yep.
Yeah, so in this case, align by function was something that they explored just to see how that fit ended up affecting the model, but then also the interpretation on the back end. So what do you think about that?
Well, I'm trying to look to see what it did. It didn't look like it cropped the points, but it looked like it kind of peanut butter spread them across that whole timeline.
Peanut butter spread. Yep.
I know.
Let me go get some fluff here. Yeah.
Yeah. So I see what it's doing, but I don't think that's appropriate in this case, given creep data and being a function of time. And we know there's a slope change on the tail. So yeah. I could see for a machine process that's repeatable, but maybe misaligned on the X scale. What else can we do?
Yeah, it sounded like you said filter or cutting some out. So that's an option there too under cleanup.
So I could remove. So under cleanup,
yeah.
I see a filter. That should be, I know if I look here, I probably don't need anything above 750. So you could just use a straight filter to crop that.
Bam. Yep.
Or I see remove, right? Interactivity.
Yeah. So this will help with those, like if you got, extreme points maybe or outliers that you want to just pull out a little bit, that remove selected works pretty well.
Got it. I like that. I'm going to go back and just do 750 here. And are we going to refit?
Refit. Yeah.
Refit. Okay. Red triangle. I know. Models.
Try the B-splines again. See what happens.
B-splines. Well, I see the mean curve didn't tail off there.
A little wiggly though still, huh?
Let me blow. We got janky on top of wonky. It looks like we're misfitting early on. Looks like we got up curves and down curves. So still not cutting it, Mr. Statsy. I need some more sophisticated tools here. What can we fix this?
We can try a different model. What do you think? You want
different model?
B-splines?
B-splines isn't working, so let's get rid of that one and go back up and fit you said the P-splines.
P-spline, penalized.
Penalized. Ooh. Hey now. That's looking like a creep curve.
TLC would be proud.
Absolutely, and we creep. And interesting, it's a step function.
Yeah, with a lot of knots.
With a lot, yeah, you don't see it displayed here. Okay, but there's like 108, 109 knots that are there that are building that functional basis model. Okay, I like it.
Sweet.
I think it's something we can use. Now, as I go back down to these mean, because you mentioned this before, but this looks a little different now, this functional PCA, and I don't know, we even know what an eigenvalue actually is. We're a shape function. That sounds way too statsy. Could you help me explain what these are?
Yeah, yeah. So that mean function's there again, and basically what you're going to be doing to get back to those original functions that you had, the curves.
So these curves, right?
Yeah. So what JMP did is it modeled them using certain different amounts of those two shape functions to get back to those red lines that are fitting those curves.
Oh, so I'm hearing you say it's a mean function plus a little bit of this and a little bit of that,
or a lot of one and a little of the
or
other.
a lot, and then that would regenerate that curve. So
can I throw a food analogy at you again?
Absolutely, you always do.
All right, you got your cookies and you got your gravy. And gravy, it's like, what is it? 3 parts fat or butter to 2 parts flour. And then you got your cookies that are like 1 part butter to 2 parts flour. So that's kind of like what's going on here is you're weighting or giving different amounts of butter or flour for the recipes. Here, you're just doing the same with the recipe for the shape functions.
I got you. Well, I like cookies and I probably want to ship some cookies in those shipping containers. So
this way.
All right, let's go. Okay, so I kind of understand what's happening here. And of course, now that I'm getting better at design of experiments, I'm familiar with this profiler. So my eyeball's going down here, but I haven't seen one like this before.
Yeah, you get to decide how you want to weight those two shape functions, how much you're adding or subtracting of each of those to get a new shape out of it.
Oh, so that's our ingredients.
That's your ingredients and how much you're adding in.
Now, quick question as I start this doesn't look like a lot there, but when I actually move it,
yeah,
start to see it impact right here in the knee when I move that. Now I know it doesn't look like it's explaining a ton of variation, but does that mean I should simplify or can I keep it or?
That's up to you. You're the subject matter expert and what those curves mean to you and what's important. I mean, you can even see that on that second shape function, that really sharp drop down, right?
Yeah.
At the very beginning. So that's basically that knee component just being represented by that second shape. So
I think it's important because that could make or break some of our shipments and the timing there. So depending on how fast that curls over. So as long as it doesn't kill my analysis, I'd like to keep it.
Yeah, you can try both ways, but at the end of the day, it's really it could be noise, but it could be something meaningful. So that's always the question.
Gotcha. Now, as I start to think about this, giving the engineers and planners a tool that can figure out how they can ship safely.
Yeah.
This functional principal components, shape functions, eigenvalues isn't going to work. I need a decoder ring, or is there a way to translate statsy speak back to common person speak so we can explain this to folks?
Yeah. So what we'll do is we'll take those experimental conditions that you had loaded up earlier, but the conduit between the curve and those will be, so under that function summaries tab there.
Yeah.
Those are the scores or weights associated with your individual curves. So if you just drop that menu down.
Oh, those are the weights of
those are the
ingredients. Got it.
And so you'll use those and you'll end up predicting those from those experimental components. So we can load those in via the red triangle option at the very top, functional DOE.
Functional DOE. Okay, let me do that. Yeah. Oh, I see some words and language that I'm familiar with. And I can kind of come back in here and now I can look at stress levels, temperature, and see how, wait a minute, I see a slope changing.
Yeah.
So when I move this, I see the slope of temperature changing.
That's your interaction, just like your standard DOE. I mean, it wasn't clear that you'd find one because of the way you set up the experiment, but you run enough runs, you may hit one by accident.
All right, we got lucky. We weren't totally off, so I'm happy to report that to the other guys on the team. So
I'll warn you, it could be an artifact of maybe that nesting of your experiment too. So I wouldn't make any general assumptions. I'd be really hesitant, but maybe a few validation runs might be helpful later on.
We still need to do this probably more robust process and design. Design something. But what I like though, this tool could be used by our loading engineers to actually say, oh, hey, I got this load condition at 6 megapascal and this temperature. And then you can kind of come back and see how far that shipment could actually go.
Yeah.
I'm going to add some visuals on this scale, Christian, just to kind of make it easier to look. I'm going to put our safe zone. I'm going to allow ranges here. And I know my upper strain value is this, and we'll add that in. And why don't I add a line too, just to make it easier to see. And this is my safe zone. So I could have a tool like this and if I'm at a really high stress level, looks like I can only ship, not very, next door, right? I'm gonna have a problem. So, but I could lower the temperature. I could rent a truck that's refrigerated. It's cheaper than using a Sawzall to unload it.
A little less fun though, Clark. A little less fun.
Or I could check out the recycled. If I used recycled, that drops everything in a safe zone. It looks like that recycled, something's going on there. Or maybe that reminds me, I could probably send recycled to Maryland and Arizona to send her orange juice. And maybe the virgin, we could pack materials and go to Canada where it's colder.
Or Michigan where she is now.
Oh, this is true. This is true. So this tool, I could actually now go back and talk with the company about, and like, here's a containment strategy for your current shipping issues here. And I think I could explain this pretty easily to the engineers that will turn around and communicate with the planners. So this is super cool. But my question is, I know they're going to say, what's next? What do we do next? And we're going to have to probably do some more experiments. And those curves that we looked at earlier, we will be doing all this stuff.
Yeah.
So how do I set up or design an experiment with curved responses in mind? Can you do that?
Yeah, actually, if you've been using the custom DOE platform already, one of the response
I've been in
options.
there.
Yeah, one of those response options is just functional data.
Oh, it's called functional, not curvy data.
Not curvy data.
Okay, but functional data there. Oh, so you can actually set that up and have a response, measurements per that, and then here are the response points. So that's awesome.
Yeah, specify your interactions in the model statement and you'll be rolling.
So we could actually design that and actually ahead of time understand, here's the types of curves. Do we want to do this ground up, right? Custom suit, like you said, or is there some other model that we might want to get off the shelf, which maybe it's a different platform and jump. So this is super cool. Awesome. Christian, now I got my brain thinking about all these other curves, whether it's, in servo motors or thermal processes. You can use this tool for anything.
I used it for baseball data about 3 years ago.
Oh, cool. And spectral, I heard. We'll get more into spectral here. There's tons of uses with that new wavelets basis function.